So here's the first of three examples of simplification and re-expansion that we're going to look at today. In this case, we're given a circuit that has three resistors and a current source. We're asked to calculate I1 and I2. Actually, it turns out this circuit's even simpler than the ones that we did in the examples because we're not going to need to do a re-expansion. We can just do a simplification stage. What you can see here is that the resistors, the 2 ohm resistor and the 3 ohm resistor, they're in series with one another. So I can go ahead and combine those two in series. I'll end up with a circuit that looks a little bit like this. So I have the 8 amp source here, and then it's going to have a resistor. And then there'll be a second resistor in parallel. And that the second resistor is the combination of the 2 ohm resistor and the 3 ohm resistor. When you combine those two in series, you simply add their resistances and you get 5 ohms. Now the question you can ask yourself is, can I label I2 as still being the current going through that 5 ohm resistor? Is this statement valid? And if you look back up at the original circuit, you can see that the 2 ohm and the 3 ohm are in series. So there was I2 was flowing here, and I2 was flowing here, and I2 is flowing here, and I2 was flowing throughout the entire that entire right-hand branch. So yes, that is still the current that you could label as going across through the 5 ohm resistor. We still have the 10 ohm resistor, and of course nothing changed about that. So I1 continues to persist there. So the circuit as we have it drawn here actually is a classic example of current division. We don't need to do any more work. We could, of course, combine the 10 ohm and the 5 ohm in parallel, calculate a single current. There would be, we'd have to label a new current. But if we did that, it would just be extra work. We're done if we just do current division. So I'm going to go ahead and do the current division here. I have that I1 is equal to the total current. That's going to be 8 amps multiplied by a ratio, which is the opposite resistor. So this is going to be 5 ohms divided by the sum of the two resistances, which will be 5 ohms plus 10 ohms. And this works out to be 2.667 amps. And then I can calculate the other current. I can calculate I2. I2 is calculated in a very similar fashion. It's 8 amps times, now we're looking at the right-hand branch, so I take the opposite resistance, which is 10 ohms, divided by the sum of the two resistances. And this works out to be 5.33 amps. There's always two reality checks that I like to do when we've done current division. I want to make sure that they add up to the original total current. In this case, yes, they do. And I want to make sure that the larger resistor has the smaller current. And in this case, yes, it does. So I'm feeling very confident that these are the correct answers. Notice that although I combined the 2 ohm and the 3 ohm resistors in series in the first step, because I2 persisted into the second version of that circuit, I didn't have to go any further. I could just use current division, and I was ready to go ahead and solve the problem.